All right. So OBS is on. We are streaming, and then we can get back to the browser. I was just talking a little bit about how I'm using a binary clock. The top bar is the hour. The bottom bar is the minute. So you just look at the top bar as a dark pixel is a 1, and then a gray pixel is a 0. That's basically how you read it. Um, Yep, so right now the top bar is 1001, which is 9. That's the hour. The bottom bar is 10, which is 2, so it's 9:02 at this point. So it's kind of one way to display the time using just base 2 numbers. It seems really awkward, but if you really want to get used to binary numbers, that's one way to kind of help you to understand binary numbers, because the first day is going to be difficult to read that. Okay, the second day is going to be easier, and by the time you get to the third day, it'll be easy. So it's really just a matter of getting used to it. All right, so we're going to get started today with a continuation of flip-flops and other basic memory devices. Last time we talked about von Neumann, who is a scientist, a mathematician, and a computer scientist, and also, a very talented person who came up with the bright idea of, instead of hard wiring, literally hard wiring, how a computer should perform its computation, why not store instructions along with the data that it has to process in memory? Then we can change the memory of a computer to change the behavior of the computer, to change how it gets things done. Okay? So that means, we first have to understand how memory works in a computer, and that's what the D flip-flop module is about. The clock circuit one is kind of interesting on its own, okay? And then we'll quickly move on. At this point, I'm basically just giving you an idea of what the pine forest looks like at this point. So very quickly, we'll get to the TTP tool chain. That's an activity. Anything that has a little space shuttle thing next to it is an activity. The TTP stands for Text Toy Processor. Literally, I'm not kidding. Okay, so that's going to be what you'll be using for assembly, for the actual assembly programming for this class. Okay, it's not a real processor architecture. You cannot buy it. Okay, and as far as I know, no one else is using that toy processor for a class like this. But the good thing about that, okay, do you guys remember, when you were, you go to a Discovery store or something like that, they sell these, engine kit that is made out of transparent plastic. It has got, working pistons and working, valves and working camshafts and stuff like that. So you can turn the engine and you can see all the valves, popping, closing and opening, and then all the pistons moving up and down, and then the engine is actually quote unquote working. That's what that is, okay? Because this toy processor is made out of components in Logisim. So you can actually look at every component and see how they interconnect, how they work together as a whole, okay? So that's the processor that we'll be using in order to understand, how a computer is organized. Because part of the title of this class is computer organization. Okay, it's not just assembly language programming, it is also computer organization. And we are working from the ground up. Okay, we are doing a bottom up type of understanding of how computers work. So this is just to give you a preview of what is coming. But today we'll just be focusing on D flip-flops and other basic memory devices. So we'll go ahead and take a look at something that we have seen already. Okay, D flip-flops and other basic memory devices. And let me see. Yep, there we go. I basically regenerated the page so that it includes a table of contents at the top. It makes it easier for you guys to navigate to the section that you want to get to. And last time we talked about the D and SR latch. So just to catch up with what we talked about last time, there we go. Okay, let me show you what is on the tablet. This was what we talked about last time. Does that look familiar to you? I hope so, because it'll be basically analyzed the operations of an SR latch. Okay, so with the SR latch, the interesting part is when both the S pin and the R pins are ones, you don't really know exactly what is Q and NQ because that depends on the previous state of the SR latch. Okay, which basically means when you look at the truth table, this is what we worked out last time, but when you read the notes also describes an SR latch. So let me switch to the SR latch notes here. So the analysis of the SR latch truth table is summarized here. When both S and R as inputs are zeros, Q and NQ are both ones. We know that for sure because of the property of a NAND gate. If at least one input is a zero, the output is a one. Okay, no big deal. When S is 0, R is 1, we know the output is going to be Q is 1, NQ is 0. We know that for sure too. That's pretty easy to analyze as well because you only need one input of a NAND gate to be a 0 for the output to be a 1. But the other one has 1, 1 as its input, and that's why NQ has a value of 0. The third row is kind of the flip side of the second row. We kind of understand that one too. The last row is the interesting part, is if both inputs with both R and S are ones, then it is no change to Q and NQ. So it depends on whether we have a transition from 0, 1 to 1, 1, or whether we had a transition from 1, 0 to 1, 1. Depending on which transition, the state of Q and NQ is just maintained. Okay? Are we doing okay so far with the discussion up to this point? Because that's where we left off on Thursday last week.
Can you say that one more time, the last one?
The last one
Yeah.
is no change. It means, if you transition from the 0, 1 state, then Q is going to be 1 and Q is going to be 0. If you transition from 1, 0, then Q is going to be a 0 and NQ is going to be a 1. Yep, go ahead.
When you say the bit transitions, you're not saying that transition is coming from the NAND gate, are you? That's before the NAND gate.
The transition is referring to the transition of the input pins. So S and R are input pins, and that's what you have control over is, I can change the state of the input pins. And what the circuit is going to do is to maybe change the states of Q and NQ because those are the output pins of the circuit. So are we still doing okay so far with this? Okay, yep.
What if I change the input pins from 0, 0 to 1, 1?
I think we did a very short analysis of that, okay? So, but it's okay to take a look at that again. And all of these you can actually put into Logisim and see what Logisim has to say about it. So we did a quick analysis of that, which is what happens when we go from 0, 0 for both input pins to 1, 1 for those input pins, and we do it at exactly the same moment, right? So what's going to happen is we analyze that circuit. It takes a certain amount of time for the gate, for the changes of the input of the gate to affect the output of the gate. So we call that a propagation of delay, okay, which is usually measured in nanoseconds, like 2, 3 nanoseconds or something like that. But the key is it takes a certain amount of time, okay? So when you first transition from from a 0 to a 1, then what happens is this was still outputting a 1, and you have this input changing to a 1. So that means both inputs are 1s to a NAND gate, which means the output of the NAND gate is going to be a 0. Exactly. So this is going to be outputting a 0, but this gate is doing exactly the same thing because the top NAND gate was outputting a 1 to begin with, and then the bottom input pin is changing from a 0 to a 1. That change will take time in order for the NAND gate to change its output. So the NAND gate is going to change its output from 1 to 0, but only after a fixed amount of time, which is about 2 to 3 nanoseconds. So in 2 to 3 nanoseconds, the output of both gates will change from a 1 to a 0. What is that going to do? Well, what that's going to do is this 0, okay, the output of the gate is feeding back to the input of the other gate. So that means the other gate, okay, from the perspective of each gate, the other gate is going to get at least one input being a 0, which means the output is going to be switching back to a 1. Okay, so but that takes another 2 to 3 nanoseconds. So every 2 to 3 nanoseconds, the output of both gates will switch from a 0 to a 1 and back and forth and back and forth. Even though the input only sees one transition from 0, 0 to 1, 1, the output of the entire circuit will flip-flop, will not flip-flop, will oscillate between zeros and ones. So that's kind of what we did, last time, but I kind of did it in a rush. So it's a good thing to kind of go over that today. Is that okay? All right. So that's a very good question because we certainly do not want, our gates to oscillate like that. So that means, we do not want to transition from 0, 0 to 1, 1 with an SR latch. Is that okay? All right. Cool. So now that the SR latch is done, going back to the notes here. So, the last part here explains, the oscillation, but in words. Okay, so you might want to read that, just to reinforce your understanding of that situation. So we are now moving on to the second design, which is called a D flip-flop. So this is once again the text representation of a D flip-flop. It has got more components, and the interesting thing is it has got the SR latch as a component inside the D flip-flop. Okay, so this is a little SR thing, which is a SR latch inside the whole thing. And we have, once again, we have input pins. There are only 2 input pins, and we only have 2 output pins, Q and NQ. But this time, in addition to an SR latch, which we see as one single component, we also have a negation gate, a NOT gate, 2 other NAND gates, N1, N2. And this is how we build a circuit. And this is all presented in kind of like pseudo C++ code, where we use the term node to refer to an electrical connection connecting ports of individual components. Look at those as wires that you draw in Logisim. Okay, so what we're going to do is we're going to draw, the pin of D to connect it to the first input of N1, which is an N2 gate, and also connecting that to N.in, which is the input of the NOT gate. So that's how we're going to make the connections. So let's go ahead and do it. And we are going to do it, let's say in Logisim. I think that would be kind of cool. And this one has been sitting around for too long, so it's swapping in from memory. Let me close it first because I don't like Logisim being stale. So we'll discard that and switch back to this one and then restart Logisim. There we go. And it's java-jar. I can't remember where I put it. Nope. Probably just the root folder. There we go. All right, so back to Logisim. I can remember certain things, so I'll go back and forth between Logisim and the nodes. So I know from the gates we'll need a NOT gate. Okay, so we need a NOT gate here. We need 2 input pins, 1, 2. We need 2 output pins, 1, 2. We need 2 NAND gates. Okay, so here's one. And let's change this one first, so then I can duplicate that. So we have 2 input pins only, and duplicate it. And then we need one SR latch. So let me see if we have an SR latch component here. They call SR flip-flop. Yeah, it's clocked. That's not what we want. Delete. There we go. It does not give me a SR latch, so we'll build one ourselves. Okay. If it doesn't have it, we'll make one. So we'll say add circuit and call this SR latch, and then we'll just build one. All it takes is go to gates, and once again we need two NAND gates, and we'll change the size and also the number of inputs. Whoops. Duplicate it. And then we need 2 input pins for the SR latch that we are building right now. And then 2 output pins. I'm just replicating the SR latch design, so this is basically a really, really quick review of what we just went through earlier. Okay, this goes here. This goes here. This goes here. This goes here. And the fun part of an SR latch is the output of one gate connects to the input of the other gate, and it's symmetric. And voila, we're done. Okay. Well, since we're here, we might as well test it, right? The inputs are 0, 0, the outputs are 1, 1s. Okay, we know that. And if we are going to change this one to a 1, okay, output is 1, 0 as input, 0, 1 as output. We know that. Now here's the fun part. If you switch the other 0 to a 1, it maintains the output. And therefore, it has the quote-unquote memory ability, okay, of not changing its output even though the input is no longer the same. Okay, but I can do the same thing with flipping this one to a 0. So now you can see how the output state has changed. But if I flip it back to a 1, that state remains. So that's kind of a quick experimentation of an SR latch in LogicSim to really kind of show you how it works. Okay, so what about that? If I change both inputs at the same time from 0, 0 to 1, 1, what's going to happen? We know it's supposed to oscillate, but how do you think LogicSim is going to react to that, right? Well, I can't do it because I cannot click the pins fast enough to be simultaneous. In other words, if I cannot click these things fast enough, as in within the propagational delay of one gate, it's not going to oscillate. Okay, so what we're going to do is to cheat a little bit. So we're going to take out one of these pins, okay, at least for now. So to take out a pin just for a moment, I'm just going to remove the wire, and instead I'll have both wires connected to the same input pin. Okay, still not a problem because as far as the SR latch is concerned, it is in the state of 1, 1, which is basically saying maintain current state, right? So that's why we are seeing a stable state for the output. So now here's the fun part. We switch the only input pin to a 0, which means we are now presenting 0, 0 to the input of the SR latch. No big deal, both outputs switch to 1. But when I switch that 0 to a 1, that is equivalent of changing both inputs to a SR latch from 0, 0 to 1, 1. And according to our analysis of the circuit, it's supposed to oscillate, right? So we'll do it here. And some people in the back may not be able to see it, but at the bottom here, it says oscillation apparent. Because LogicSim cannot actually do the oscillation, but it can detect the oscillation. So that's kind of a confirmation of how you can trigger an oscillation with an SR latch. So is that okay? All right, cool. All right. So with this done, we're gonna fix the circuit. Okay. So we'll go ahead and fix the circuit. And I think in this case we have to reset simulation. and then we'll fix the circuit back to where it was. Delete this, hook this one back to here, and we have to switch to edit circuit appearance so that we can look at it as a chip. And it's always good to label the pins. Okay, so we have S. Now, S is really, it should be a /S. I will explain why that is the case. Even though a lot of times we do not use the slash, having the slash is actually a lot better. And the Q is the NQ or not Q is now /Q. So let me move all of these into the right place, and then I'll explain why there's a slash, or what the slash actually represents. All right, there we go. Put everything inside onto the chip so it doesn't use up any extra space. It's all good. All right. So the slash, when you look at what we call data sheets of chips, a slash or overbar means negation. It means not, okay? So why are we putting a slash in front of the S? Why are we putting a slash in front of the R? It means those particular inputs are known as active low inputs. Because we normally say a 1 means we want that, a 0 means we do not want that. A slash means no, it's the opposite. Okay? When S is a 0, we mean we want to set the latch. When S is a high, that means we are not setting the latch. S stands for set, R stands for reset from the perspective of Q. If you're setting a latch, Q becomes a 1. If you're resetting a latch, Q becomes a 0. Is that okay? So a 0 presented to /S is going to set Q. A 0 presented to /R is going to reset Q. So that's why the naming of the pins has a slash in front of it, because those are active low input pins. Which means when it is a 1, we don't want to do it. When it's a 0, it means, yep, go ahead and do that. Those are called active low input signals. Q, on the other hand, has a non-negative version, which is Q. But the negative version, instead of saying it is not Q, we just say it's a /Q, because slash, once again, means negation when it comes to the documentation of pins of chips. Is that okay? All right. Most of you will not need to actually use these nomenclature except for the computer engineers. So as a computer engineer, you probably will have a lot of time to read data sheets of various chips. So understanding the notation of these pins is going to be helpful. All right, so we are done with the SR latch. We can now go back to the main circuit, and we can just now go like, okay, give me one SR latch as a component. Cool. Right? Okay, so now the question is, how do we hook up all these pins? So we're going to have to switch back and forth a few times. So we got N, N1, N2, S, R, D, E, N, Q, and NQ. Okay, so going back here, we'll start to label these things. So I think one is D for data, and one is EN for enable. I don't think we can give a name. Oh, we can. Okay, so this is just N, which is the NOT gate. The two NAND gates, they're labeled N1 and N2. I'm doing this just so that the diagram is completely corresponding to the text. And then the output pins is still the same thing. One is Q. And I'm going to change the other one. Instead of using NQ, I'm going to use /Q, which means exactly the same thing as the negation of Q, but we're using the slash as a negation symbol. The SR latch, we can actually have a label for that too. It's just SR. But it makes it difficult to read because it's actually here and it is rotated like that. So it's a little bit hard to read. All right, so with all of these, now we look at how the components are connected. So the first node is connecting D to the first input of N1, but also connecting to the input of the negation gate. Okay. So that goes to N, but it also goes to one input of N1, but which one is it? The first one, okay. Okay, that's the first node. And let's see. The second node is going from the En to the second input of the first NAND gate, but also the first input of the second NAND gate. Okay. So En goes to here and also here. There we go. Let me just double check. Yep. The output of the NOT gate, okay, we are reading the third node here. The output of the NOT gate goes to the second input of the second NAND gate. So, okay, this is going to look a little bit ugly. Looks up like that. And then the output of the first NAND gate goes to the output of the first, the S of the SR latch. So here's the SR latch, like so, and like so. And I forgot two things. I forgot about the output pins in the text description. So the Q goes to the Q, the NOT Q goes to the NOT Q. So those were missing in the text description. So this is our new circuit to analyze. And let's go ahead and let's not enable simulation. We'll keep the simulation turned off so that we can just look at this and try to analyze it manually, okay, without actually running the circuit. And we'll go ahead and zoom in one more time. There we go. All right. So the question is, as long as En is a 0, what is going to happen to the outputs of the NAND gates? And what's going to happen to the SR latch? That's the first thing we want to analyze. When En is a 0, okay, regardless of D, okay, forget about D for now. As long as En is a 0, what's going to happen to the SR latch? Okay, En goes to N2, but it also goes to N1, right? So the outputs of the NAND gates will be 1s. Very good. So if the outputs of both N1 and N2 are 1s, what's going to happen to the SR latch? Nothing, right? It will maintain its state, okay? No change to the SR latch. So that means as long as En is held 0, nothing is going to happen. You can do whatever you want with D. Doesn't matter at all. Is that making any sense? Okay. So what if I change En to a 1? Well, let's think about that, okay? If you change En to a 1, that 1 is going to N1 as well as N2, which means the output of the NAND gates will now only depend on the other pins. Okay? Is that making any sense? When En is a 1, then the output of N1 only depends on what D is. The output of N2 only depends on what the negation of D is. Is that okay? So now it becomes sensitive to D. Don't you think at least one of these two NAND gates is going to be a 0? Because one is receiving the negative version of D, the other one is receiving the non-negative version of D, so one is going to be a 0. So let's imagine that D is 1, okay? So En is 1, D is 1. We know that the output of the NOT gate N is going to the second NAND gate. So if D is 1, then the output of the second NAND gate is going to be a 0. Oh, it's going to be a 1. Yeah, you're right. It's going to be a 1, which also means /R is going to be a 1. If /R is a 1 according to the label /R, are we resetting the latch? What does the slash mean? negation, but in the case of an input pin, it also means that input pin is active low. Active low means it is inactive when it is high, which means when there's a 1, we are not doing a single thing. Okay? Let's look at the top NAND gate, N1. D is 1, right? So D is 1, which means the first input of N1 is going to be a 1. En itself is a 1, which means the second input of N1 is also a 1. We got 1, 1 going into a NAND gate. What is the output? A 0. That 0 goes to /s of the SR latch. What does that mean? When /s is a 0, what is the SR latch supposed to do? Change Q to a 1, okay? So we're expecting Q to become a 1. And then the moment you disable En, which means you're switching En from a 0 back to from a 1 back to a 0, it will just maintain the state. Doesn't matter what you do with D at that point. Is that okay? So this is called a D flip-flop, or the simplest form of a D flip-flop, which basically changes the main change from a regular SR latch is, instead of having one pin to say set, the other pin to say reset, now we change it to also use 2 input pins, but now one is dictating, are we changing? And then the other one specifying, what are we changing it to? So that is the change between an SR latch and a D flip-flop. So let me say that one more time, because the difference is kind of significant. An SR latch, which is a very, very simple device, has 2 inputs. One input says, are we setting? The other input is saying, are we resetting? In order to change the state, you have to say, we are setting, or we are resetting. That's how you use an SR latch. A D flip-flop, on the other hand, is saying, are we changing? That's En's job. It's saying, are we changing the state of this device? And then the job of D as an input pin is to ask, if we are changing, what are we changing the state to? So can everybody see the difference between an SR latch, which is a simpler, very simple device, as opposed to a D flip-flop, which is a little bit more complicated, but the perspective is now different? Is that okay? Which one would you prefer? D flip-flop is more useful because now you can just say, what is the data that we are storing and when are we storing it? As opposed to, oh, are we setting it or are we resetting it? Is that okay? So this is also called a gated circuit. It's called a gated circuit because the job of En is kind of like a gate. It's saying, are we changing or not? Because when En is a 0, we are not changing anything. D can change all it wants, but nothing is going to happen to the SR latch as a component of the D flip-flop. So that's why En is also known as a gate. And this is also called a gated circuit. So are we good so far with the simplest form of a D flip-flop? Okay. Well, let's go ahead and run it, right? Because I have the circuit already here, might as well enable the circuitry to run. Now the output is E here. That's because we haven't really worked with it, and we switched directly to 1, 1, and without going through one of the known forms. And that's why the D flip-flop the SR latch doesn't know what the output states are supposed to be, because it went from unknown for both inputs to 1, 1. 1, 1 simply says we'll maintain the current state. But when both inputs were unknown to begin with, the outputs were also unknown. In other words, you're asking the SR latch to maintain the quote-unquote unknown state. And that's why we get the errors here. But that's okay, we'll fix that. First of all, let's go ahead and play with the D pin. Okay, we can flip it all day long and nothing happens to the SR latch. It is still in an error state. Okay, fine. Let's do it En. Ding. It instantaneously changes the state of the SR latch according to the D pin. So the D pin is a 0, so Q is now a 0. Slash q is really just the negation of q, so we usually do not pay attention to slash q. Is that okay? So now at this point, I can say, okay, I have changed the SR latch to what I want. Let's not do any further changes. I turn off enable. Now I can go to D and just keep clicking it, and nothing happens to the SR latch because it is not enabled anymore. It is not going to make any changes. What if I want to make changes again? Well, turn on enable, turn D to whatever state you want to change the SR latch to, let's say to a 1. And then you turn off the flip-flop again, so now the state is locked. Is that okay? So that's okay? All right. So this is a D flip-flop, or the most basic form of a D flip-flop. But if you read the notes, there are more D flip-flops. So section 5 talks about an edge-sensitive D flip-flop. And this one is a little bit more complicated. You can see that this time we have 2 SR latches, not just 1. On top we have 1 3-input NAND gate, 1 2-input NAND gate. We have only 2 input pins just like before. We have the clock and the data as input pins. We have 1 single output pin Q, but the nodes gets a lot more complicated because we just have a lot more components to deal with this time. All right? So let's go ahead and construct this particular circuit and see what it does and how it gets the job done. So we switch back to this one, and we'll go ahead and make a new circuit. So add circuit, and we'll call this one a clocked D flip-flop. And if I remember correctly, we got a few gates that we need to put in here. We need 2 NAND gates. So we'll just go ahead and make 2 NAND gates here. One is a 2 input. Okay, let me see which one is a 2 input. So the 2 input is N2. So this is going to be our N2. And it's going to be a 2 input. NAND gate. And make it smaller. There we go. So this is going to be our 3 input NAND gate. Like so, and we call it N1. Okay, what else do we need? We need 2 input pins, 2 SR latches, okay, clock and data. Okay, so we have 1 input pin called data, and another one called clock. I'll just abbreviate it to CLK for clock. We need 1 output pin named Q. And then we have 2 SR latches. So we just go to our SR latch component that I just made recently. And we set 2 of these things here. It becomes kind of difficult to see the labeling. But this time I think the names are simpler. C, S, and C. Okay, so we'll name the first one S, and the bottom one C. Like so. Oop. Oh, this is a shared label. Okay, so we have to use the non-shared label for this. So this is S, and get rid of the C because that's not needed. The other one is called C. Whoops, wrong place. Here. No. Get rid of that. There we go. All right. So I think we got all the components. And now we just have to make the connections. All right. So the connections is going to look a little bit ugly because we have like 5 nodes to deal with here, 6 nodes. The first one is just going from the data pin to the second input of the second NAND gate. Okay. So I might want to exchange the position because that just seems like it's a better idea to do it like this. Okay. So that takes care of the first line. The second line connects the clock pin to the second input of the top NAND gate, but also S.R. Okay, so the R of the S flip-flop will receive that. So the clock pin goes to the second input of the first NAND gate, but it also goes to the R input of the SR latch. Let me just double check, make sure. Okay, clock pin goes to R of S and also going to the second input of N1. Second node is done. Third node. The third node takes the output of the second NAND gate, connected to the last input of the first NAND gate, and also connected to the S pin of the SR latch. Okay, so of course I have forgotten half of what I just read. I think I remember this part. Okay, so we got that, and also go to SS. Okay, there we go. So this one also goes to here. Okay, so the third node is done. Now we're on to the fourth node here. The fourth node takes the output of the first NAND gate, connected to the first input of the second NAND gate, but also to R of the CSR latch. So we take this output, and then we hook it up to here. But it also goes to R of C. Okay, so R of C is this thing, and we also want that to connect there. Okay. We're on to the fifth node. We take the NQ, or the /Q of S, and connect it to the S of C, but also to N0 of N1. So that's the first input of the first NAND gate. Okay, so we take this to connect to this pin. That's the first connection, but we also want to hook it up to C.S. So we also want to hook this up to C.S. like so. Onto the last node. The last node is to take C.Q to connect to the actual output pin of Q. All right. Done. Whew. Okay. Yep. Oh, okay. Thank you. So we have to undo this and hook it up to the bottom one. Thank you. All right. So we're done. Well, what do you think this circuit is going to do? This one is a little bit more complex to analyze. So what we'll need to do is to look at, look at the circuit from the perspective of different scenarios. And all of those scenarios were described in the notes. So if you read through the scenarios, we'll focus on 5.1 first. So 5.1 says the data is 0, the clock has a rising edge. What does it mean when I say a rising edge? A transition from a 0 to a 1 is called a rising edge. A transition from a 1 back to 0 is called a falling edge. So you have a rising edge from 0 to 1, and the falling edge is from 1 to 0. Those are all referring to transitions. Okay? All right. So looking at this diagram, and we want to go back to the circuit also, but we'll disable simulation for now so that we don't get tricked by the coloring of these points. So we want data to be 0, but we also want clock to go from 0 to 1, okay? And, well, the first thing is, what if both are zeros? When clock is 0, and it's going to force N1 to be, the output of N1 is going to be what? A 1. When data is 0, it's forcing the output of N2 to be a 1 as well. So N1, the output of N1, eventually goes to the /R of C, but when it's a 1, it means it is not resetting. The output of N2 goes to the S of S, but since it is a 1, we are also not setting. What about the other pins? What about the other 2 pins to control the SR latches? Let's see. So we look at this. Let's look at /R of S. /R of S is connecting to the clock pin directly. So that means /R is now a 0. And what does that change? What does it do to the SR latch? No. We are asserting /R because /R is a 0. So, and the slash means it's active low, right? Is that pin experiencing a low voltage at this point? It is, right? So what does it do to Q? It will reset Q, but that means /Q is going to be a 1. So /Q is going to be a 1. The 1 goes into the /S here, which means there's no change to the C flip-flop. No, excuse me, there's no change to the C SR latch. Is that okay? All right, so let's go back to the text description of the analysis. So it says right here, S.R is a 0, and it causes C.S to be a 1, which means we are not setting C. N1 dot in 1, which is the second input of N1, is a 0, and that's causing C.R to be a 1. So the SR latch C is maintaining its state. Okay, so going back to this circuit, this is maintaining its state. So what happens when the clock pin is switched to a 1? Data pin is remaining a 0, but we are switching the clock pin to a 1 at this point. What is going to happen? So clock is switching from a 0 to a 1, okay? So that means this input of N1 is going to be a 1. To understand what this N1 is going to output, we have to look at the other inputs too. The first input of N1 is connected to /Q, and what is that again? It's a 1. So we have 2 1s. What about the third input to N1? That connects to the output of N2, and the output of N2 is also a 1. So that means all 3 inputs of N1 are 1s, which means its output is going to be a 0. Where is that 0 going to? It goes to 2 places. The first place it goes to is /R. /R of C, the SR latch C. So what is that going to do to the output of the C SR latch? The /R is a 0, which means we are resetting the SR latch. If you reset the SR latch, what happens to the output? It changes it to a 0. When you reset, it changes to a 0. When you set, it changes to a 1. So we are expecting Q of C to become a 1, okay? But that is also going into the input of N2, and that's a 0. So now we have 0, 0 going into N2. The output of N2 now becomes a 1. That 1 is going to S/S, which basically is not doing anything to the SR latch. But the output is changed. The bottom line is, at that particular moment of switching clock from a 0 to a 1, the output of the C SR latch will change to a 0 if it was not a 0 to begin with, because we are resetting it. Is that okay? So now what we do is we simulate, okay? We run the circuit in Logisim and see whether that is the case or not. So we click simulate, we enable simulation, and it's error because we did not specify what the state was. With this SR latch, we are only telling it to maintain the state. We're asking the SR latch to do the impossible, maintain the unknown state. So the SR latch is going to say, I don't know what the unknown state is, so it's just reporting error here. Okay. So when we switch clock from a 0 to a 1, only at that particular moment are we going to change the output of the CSR latch. So we go ahead and make that change. And you can see how the CSR latch is now changing its output from unknown to a 0. Okay? So that seems like a lot of steps to do to kind of do the same thing that we did in the previous D flip-flop, right? So now the question is, what if the clock is to go back from 1 to 0? What do you think is going to happen? So this time we'll just look at this diagram because it has the current state. We just have to kind of think about, what if the clock goes from 1 back to 0? What's going to happen to the rest of the circuitry? Well, this one is going to switch back to a 0. The first thing it's going to affect is N1, because N1 currently has 1, 1, 1 as its inputs. Now, in the next moment, it's going to have 1, 0, 1 as its input, which means the output of N1 is going to be a 1, because if at least one input is a 0, the output is going to be a 1. So that change is going to change here, which also means this is /R, which is now a 0, is going to be a 1. Would that make anything change with a CSR latch? Nope, because the CSR latch will have both inputs being a 1, which just means maintain state, don't do anything, right? But that one is also going to change the first input of N2, but N2 still has 1, 0 coming in from the second input, which means the output of N2 is going to maintain, it's not going to do anything either. Is that okay? So now we do it, okay? So now we actually go ahead and do it, and you can see that nothing is happening. Is that okay? Okay, so now let's do another exercise. The other exercise is to replicate the scenario that we were in, and we say, okay, is this clock pin doing the same thing as EN from the previous design? Which means if I go change your data right now, the output of the CSR latch is going to change too? That's the question, okay? So what we want to do now is to say, what if we change data from a 0 to a 1 right now? Is it going to change the value or the output of the CSR latch? What do you think? Well, let's not think, let's analyze, right? Let's go ahead and actually work this out. Data is going from a 0 to a 1, okay? So this goes from 0 to a 1. Is that going to affect anything? It is not affecting anything at all, because N2 has the other input, the first input being a 0. So even though you're switching the second input of N2 from a 0 to a 1, it doesn't change the output of N2 at all. So if the output of N2 is not changing, the changes from the input pin stops here. And no further changes is going to be visible within the circuit. Is that okay? So let's go ahead and do it. I mean, we always want to have a little confirmation by doing it. You can see how I can now change the data line without actually changing the output of the CSR latch. But that is kind of cool, because this means there's only one moment in time that the output of the CSR latch is going to be affected by the data pin. It's only when CLK, or the clock, is transitioning from a 0 to a 1. Okay, so there's a very short amount of time, there's a very short moment in time when the circuit really pays attention to the data pin. Other than that moment, during that transition, it doesn't pay attention at all. Data pin can go 0, 1, whatever it wants, and it doesn't care. Is that okay? So that window of time is related to the propagational delay of these gates here. So I would say it's probably in the order of maybe 6 or 7 nanoseconds in this particular case. So it's a very short window of time that it actually pays attention to the input pin data. All of the other time, it ignores data. Is that okay? Okay, fine. Since it is sensitive to the change of clock pin, let's do something like this. Let's change the data to a 1, and then we say, what if I change the clock from a 1 back to 0? Because that's another transition, right? And according to the design documentation, it's supposed to be only sensitive to a rising edge of the clock. It should not be sensitive to the falling edge of the clock. But we want to analyze the circuit to make sure that it is not sensitive to a falling edge of the clock. So now what we do is we look at this circuit and go like, what if clock goes from a 1 back to a 0? Will the output of the C flip-flop change at all? That's the question. So what do? Well, we look at the change, and then mentally we follow the change and propagate that change throughout the circuit. So we look at clock, it goes from a 1 to a 0. First thing, it affects several things at the same time. First of all, it affects N1. Okay? N1 is going to have one input being a 0, but because it's a NAND gate, the output will become a 1. That output goes to 2 places. The first place it goes to is /R of C. That's okay. You can turn the inputs of the SR latch to 1s and it doesn't do anything. Okay? All right, so it has no impact to the C SR latch. The second thing that the output of N1 affects is the input is N2. N2 right now is outputting a 1, and because both inputs will become a 1, N2 will now output a 0. What is that going to do? When N2 outputs a 0, it would affect /S, so that /S will go from a 1 to a 0. Okay? Which also means /Q is going to go from a 1 to a 0, from a 1 to a 0. So that's going to come back here, and it's going to do a /S will become a 0. That's going to affect the output. Am I missing something?
The first pin of NAND 1.
Huh?
The first input pin of NAND 1 is the other result
Uh-huh.
of /Q from S.
Right, so this will change to a 1, but /R changing to a 1 is not going to affect anything. I'm more concerned about this connection here. Okay, let me analyze this one more time. So clock changes from a 1 to a 0. N1 changes its output from a 0 to a 1. Okay, that's okay. And then this one also goes to N2. The output of N2 becomes a 0. That 0 goes to here, which changes the output of S to a 1, which means the negated of the output is going to be a 0. That 0 is going to go back here, which is going to set the output of C. So it does change Q, which is not what the circuit is supposed to do, because it's not supposed to be sensitive to a falling edge. Yep.
But doesn't clock also change go to the S? Yeah.
It goes here. Yep.
It changes that to 0.
So that will change. It's going to change this to a 0, which means /Q will maintain to be a 1. Yep. Say that one more time. N2. Correct. Well, N1 is going to be N1 is going to output a 1 regardless, because clock is going to be a 0. Because the transition is the clock going from a 1 to a 0. So the problematic connection that I see is this wire here because I don't want this to be low, but because it hooks up to this wire, slash Q is going to be a 0 because Q is going to be a 1, and that's because slash S is going to be a 0, which is coming from here. So the circuit is not going to work the way that I thought it would. Well, let's first of all, let's do that first, just so that I can see whether the circuit changes. Nope. Okay. Huh. It didn't change the... It changed the output, didn't it? Okay. It changed the output, but that's because of my own doing. So let's reset the whole thing. Okay. Change everything back to what it was. Okay. So now we change the data to a 1. And then we want to change clock from 1 to a 0. And we want to make sure that the output of the C SR latch does not change. Okay, there's something wrong with my analysis. The circuit did what it's supposed to do. Yep.
The output of N2 is going to be a 0, but also, and N2 goes into slash S. Also, clock is going to be 0, and that's slash R. So when S of S and R of S are zeros, doesn't that make slash Q also 0?
That's right. Okay, that's what I've...
That makes Q a 1.
Yes. So slash Q is going to be a 1, which maintains what it is right now. Thank you. That's what I missed. Because I look at only this one, but I forgot to look at slash R. I need to look at both of those, because if slash R and slash S are both zeros, then both outputs of the SR latch would be 1s, which means it is maintaining its output to slash S of C. Thank you. That's what I have been missing. Because I look at one single pin and go like, but that's going to change. No, you have to look at the other one too. So I forgot to look at both pins of the SR latch. Thank you. All right. So what is the bottom line? Okay, we have been digging around in the pine needles for a little bit. So when you look at the pine tree, what is the pine tree saying? Okay, so forget about all of these things in the middle. Okay, so look at the clock, data, and just Q itself. Okay, so everything in the middle is really just a pine needle. But when you look at the pine tree, how is this design different from the design, the previous one? Okay, let's go back to the previous one. Play with that for a little bit first. Okay, so we look at the previous one is still called main. Okay. In the previous one, as long as En is a 0, you can flip, D, and nothing changes with the output. But the moment you change En to a 1, then the circuit becomes sensitive to D. Okay, this is also what we call level sensitive D flip-flop. Okay, and then when we go to the new design, okay, we go like, well, the change only occurs. It only samples data when clock is transitioning from 0 to 1. So if I go from 0 to 1 at this point, Q is going to change to a 1. Okay? But other than this moment, okay, I can now change data any way I want, and nothing happens to the Q, right? I can change clock back to 0, and I can play with data all day long, and nothing changes Q. So what is the change? From the perspective of just the pins, how they interact. What is the one big difference between a clocked D flip-flop versus the previous simplistic D flip-flop? Exactly. Exactly. So this particular circuit only updates the output at the moment that the clock transitions from 0 to a 1. Only at that moment it will look at the data input and update Q of C accordingly. Any other moments, it doesn't pay attention at all. Is that okay? So it has a very narrow time frame that it actually pays attention. Okay, so if I were to use an analogy, with students, okay, you guys are all the original, the other D flip-flop. As long as it is enabled, which means you're in class, you're paying attention to what I'm saying. Okay, so it's continuous. Okay, when I say something, you're registering that, and it keeps going like that. With this circuit, it's almost like this. When I clap, you only pay attention during that moment, which is not good in the class. It's only when something happens then you pay attention, and then the rest of the time you're ignoring everything that I'm saying. Okay, now a clap is kind of not a very good analogy because a clap is kind of a rising edge followed by a falling edge. So, but this is even more specific. It's only on a rising edge that it will pay attention. Is that okay? Are there any questions about the pine tree called a clocked D flip-flop? No questions? Okay, you have a question of some kind.
Just trying to relate this like in a different way. So, kind of like the difference between you walk into a hotel and there's the attendant that's at the desk. If with the regular
D flip-flop.
flip-flop, that they're just waiting for you to come up to them. Whereas with the clock one, they're doing something else until you go up and ring the bell, and then they're waiting to help you.
It's not really that, because if the ring of the bell is a rising edge, then they only listen to you at the moment that you ring the bell. As soon as the bell is not ringing anymore, they go back to their own routine and ignore you.
How about when you say something in high pitch, and then we will notice that. And then when you say something in normal, just like zero, and you do not, you ignore. When you are yelling, just like zero from one,
Mm-hmm.
from one to zero, from zero to one.
That's a rising edge.
When you are yelling, so you pay attention.
But only in a transition. That's the whole thing. It's not when I'm yelling. It's only at the moment that I start to yell. If it is while I'm yelling, it will still be level sensitive because it is for the entire duration that I'm yelling, which means it will still go back to the original D flip-flop. It's when the enable line is a 1, then you keep paying attention to the data line.
So what's that specific moment?
Yeah, this is only a very specific moment. It's only when the clock is going from a 0 to a 1, then you pay attention and you mirror at that moment what data is as an input pin to Q as an output pin. Any other moment, it doesn't pay attention at all. So I can't find really a lot of real life analogies for this particular example. Is that okay? Okay, so if we zoom out even more, okay, if we zoom out one level, and just say, okay, so if I have one thing that I need to take away from this class, what is it? This limits the time when the D flip-flop pays attention to the data line. It's only during that moment when the clock line has a transition from a 0 to a 1. Yep.
Got it.
Yep.
Camera.
Okay. Okay. Go ahead.
So the data is whatever you're pointing the camera at.
Mm-hmm.
The output is whatever you're going to get as the picture, and the clock is as soon as you press the button on the camera.
Shutter release.
Only looks at that one moment.
Okay. So as a photographer, as an amateur, or in British term, amateur. Okay, as an amateur, photographer, the shutter is actually a enable. It's not a edge sensitive, because as long as the shutter is open, it will continue to register light. So when you look at the camera, the shutter release mechanism is actually closer to the other D flip-flop than an edge-sensitive D flip-flop. The only one thing that I can see that is truly edge-sensitive is a little bit sensitive, because I don't want to use it as an example in class, but I think it is actually the best real-life mechanical example of something that is edge-sensitive and is a one-shot kind of thing. Okay, so I'm gonna use that example. Okay, if people feel uncomfortable, then I won't talk about it. It's the same thing as a trigger. Okay, of a non-automatic gun. So you cock it, okay, and you release the safety, but the moment you pull the trigger, only at that moment will it do something, will fire. But after that, you can keep pulling it, okay, release, pull, release, pull, release, pull, and it's not going to do a single thing. It has to do with the same kind of mechanism of a state being held, and then you have a transition here that goes from one state to another state, and only at that moment it's going to do something, and then it's not going to do anything afterwards. So that's the best example I can think of, that for something that is truly edge sensitive. But there's nothing else in real life that I can think of is actually edge sensitive. Yep.
So, why would an edge-sensitive circuit exist? Like, it seems like.
Why do we need it, or why does it exist? The reason why it exists is just explained here.
Well, why would we need an edge-sensitive circuit?
That's a very good question. Okay, so it has to do with something like this, okay? What if you need a circuit that counts? In other words, okay, somebody walks through the room, click, it goes from 0 to 1. Another person walks through the door, you click again, it goes from 1 to 2. So that clicking that you're doing is producing the edge. But you need something that does all the counting, right? So even with all the circuitry that we have talked about, the adder thing, how do you connect an adder in a way so that it can count? What does an adder do? Okay, so abstractly speaking, what is an adder going to do? I'm switching to the tablet. So an adder doesn't do a whole lot. So, okay, so abstractly, okay, so we'll just say that you're presenting 17 to an adder, and the adder is going to output 18. Okay, that's all it's going to do. So now the question is, how do you make it increment? Well, you can say, well, what if we do it like this? Then it will continuously increment, because every time the input changes, it's going to adjust the output. So this is going to keep changing the output depending on the input, not when you click, not when you say when. Is that okay? Which is not what we want. Yep. So we need the concept of a clock in this case is basically asking, when do we update? Okay, but we need something in between. So what we need in between here is a memory device. So we need a memory device in between that maintains the previous output of the adder, but only when you click, when you have an edge, when you have a transition, then it would update itself based on the adder. That is the reason why we need edge-sensitive circuitry and not just level-sensitive circuitry. Now, what if we use a level-sensitive circuitry instead? Well, as long as your hand is still on the button, it will keep incrementing. Is that okay? That's not what we want either, because if you are the person who is counting how many people have entered the room, you want that clicker to only increment when you are pushing it down, not when it is held down, not when you release it. That is why it is important to be edge sensitive. Okay? At this point, with only an edge sensitive D flip-flop, we can't quite do this yet. Okay? So we'll need to rely on some additional circuits. We got 4 minutes, so we can move on at least introduce the additional circuits. So let me switch back to the browser here. So the next circuitry is both clocked and gated. So it has 3 inputs instead of 2, and only 1 output like this. Now we are not going to do a whole lot of analysis at this point because these gets actually pretty hairy to analyze. But this one has got 3. It has got data, enable, and clock. It only has got one output, which is Q. So it is both edge sensitive and gated at the same time. If enable is off, nothing happens. Even if you have a rising edge with a clock, nothing happens. So the only time that it will update the output is now when enable is a 1, level sensitive, and clock is going from a 0 to a 1, edge sensitive. When both of those conditions are present, then whatever data has is now going to be reflected at Q. Okay? Now, why do we want something like this? If edge sensitive is already enough to make that clicker counter thing, why do we need this enable? Because you might have the same clicker, connected to different counters, and you want to say which one is going to increment. Is that okay? Okay, let's say you're at Costco, okay, and you need to count the number of members versus non-members, people who present a card versus people who are following people with cards, okay? But you only got 1 clicker. You go like, well, with 1 clicker, how do I maintain 2 different counters? Well, you have 2 enable pins. In other words, there's a little pedal, okay, on the floor. If you step on this lever first and then click, it increments the member counter. If you step on the other lever first and then click, it increments the non-member counter. So this is how you can maintain 2 counters with only 1 clicker. With 1 single clock, you can now say which counter increases. That's what the enable is. The enable is the pedal that let you select which counter is going to increment, and there's only 1 clicker, which is your clock. Is that okay? Now this is very important because inside a processor, you have a lot of stuff going on, okay? But you don't want to have a route to go from every single component to every other component because that's just impossible to do. So what you need to do now is to have these devices to share. But if you have devices to share, then you have to say, oh, there's a lot of traffic going on, but I only need you to pay attention when you are told to pay attention, and only when there's an edge. That's why we need both the edge sensitivity and also the level sensitivity, because this EN allows us to specify who is paying attention. The clock is now letting us to specify when that thing is going to pay attention. So now we have control over both who, or whom, to be correct, whom and also when to pay attention. Okay? So that's really kind of important. We'll go over these concepts again next time, but I just want to kind of fast forward because I want you guys to study a little bit or read ahead of me before Thursday. So the last one is is gated, clocked, and resettable. Okay, so there's one last pin here that was missing in all of the other design. There's a reset button. The reset pin is also very important from the perspective of a real circuitry. Because when you power up a computer the first time, what do you think is going to be the state of your SR latch? We don't know. It is undetermined. So that's why you need a reset pin to basically say everything in the computer reset to your quote-unquote default state. So now your computer has a known default state to start with, which is very important. So that's why we have a reset pin with the last D flip-flop, so that it is resettable, gated, and edge sensitive all at the same time. All right. So we are running out of time right now. We'll continue this on Thursday, but please, please, please read ahead of me, so that you understand the circuitry at least up to this point. So today at the lab, I think we're just going to continue with the positive exponent homework. So if you're done with that one already, I don't think there's anything else you need to do.